So one of the possibilities, and I'm talking about a closed system. And the word closed is going to mean that the system is not allowed to oscillate at the ends. Both ends are pinned. No oscillation. Close, close, both ends. So if that's the case, then the kind of standing wave patterns that you could have is, as we discussed before, one half wavelength, right, corresponding to a pattern where it goes up, then down, and just one up and one down. So that will look like this. So this distance, let's say that this distance, it's a guitar, so the distance between the bottom and the top is fixed. You can move that. This is L. It's a guitar string with length L. This is the first pattern that you can think that would satisfy the condition. No oscillation here and no oscillation here. Right? So the standing wave, it's in all cases described by this. The fact that there's no oscillation, let's say that this is the x-axis wrong here. And that's the displacement axis. There's no displacement here. That's nicely matches the fact that this is a sine kx, where x equals 0 gives you sine 0. So that gives you displacement equals 0. So that's fine for this end. But we need to make sure that the other end also has 0 displacement. Okay? So that means that we're going to have to make sure that the sine of KL, when x is equal to L, you're over here, that is equal to 0. Right? Because we know that the displacement when x is equal to 0 at any time should be equal to 0. Let me write this a little bit better. It's 2a sine KL cosine omega t. That should be equal to 0. Therefore, sine of KL equals 0. K is the wave number, and that's 2 pi over lambda. Therefore, 2 pi over lambda times L, the sine of this should be 0. So what angle should that be? This angle, the argument that goes here, being 0, we already covered that. Don't consider that one. What other angles satisfy the condition? Sine of this equals 0. The sine of what angle is 0? Pi, right? What other angle gives you sine 0? We already said 0, pi, 2 pi also, 3 pi, 4 pi, etc. Right? So this, if that is equal to any multiple of pi, you're good. So the wavelength, you can put a little index n here to indicate the different wavelengths of the traveling waves that you can set up in your system that will fit nicely in the length of the system that you have to produce a standing wave pattern. So those wavelengths are going to be equal to this. Cancel the pi. They're going to be 2L over n, right? And the frequencies to go along with that, because frequency and wavelength are related through this equation, the velocity of the wave connects the two. Then the frequencies should be equal to what? N, velocity, divided by 2L. Just replace this here and solve for frequency. So the picture that you see here is the picture corresponding to n equal 1, where the wavelength is equal to 2L. Do you see that the wavelength of this wave is 2L? This is L. This is only half a wavelength. The other half will be over here. So the wavelength is 2L for this particular mode. We call this, for the different ends, we call them modes. That's mode number 1, or fundamental mode. Let me write it here. This guy is the fundamental mode. But there is other modes. Just to draw a few other ones. This is L. Another one that you could have is, instead of 1, 2 sections, or as I call them, humps. So that's L. So you have 2 of them, right? So we're talking about n equal 2. And the wavelength corresponding to that mode is 2L divided by 2, which is equal to L. That's one complete wavelength that you can fit there. And the frequency corresponding to that, F2, is, put in number 2 on that equation. N is equal to 2. So that's 2V divided by 2L. And that's V over L. And then n equal 3, which is the one that I showed you over here when we had the bifrequency. That was n equal 3. And the frequency, lambda 3 would be 2L over 3. And frequency 3 would be 3V over 2L. So notice that in general, frequency of the nth mode for this kind of systems is n times the frequency of the fundamental mode. These guys are called the harmonics. And for a system that is closed on both ends, it's all the multiples of the fundamental frequency. N can be 1, 2, 3, any number that you wish. So a guitar string, when you pluck it, you would hear mostly n equal 1 mode, but there will be a little bit of other modes, n equal 2, n equal 3, and so on. And this particular combination of the harmonics that you hear when you play an instrument, that's what allows your ears and your brain to distinguish between, a C note played by a piano and a C note played by a violin. They both might be having, they both would probably be oscillating with a fundamental frequency that is the same, right? But there will be a little bit of this n equal 2, n equal 3, n equal 4 added into this mixture. And that's the kind of information that allows your ear to distinguish the different sounds. So that quality is called the timbre, and it has to do with the combination of harmonics, the particular frequencies that are present in a sound. Yeah.
It's only plastic closed.
Right. So we're discussing closed systems. Right. So there's other systems, because I could create a standing wave pattern here. I don't know what exactly the frequency would be here. So, but I could just unpin this side, let it oscillate freely, and start scanning here with different frequencies until I get a nice standing wave pattern. Like I said, I didn't do that, but I could do that. So in that case, I'm talking about a different system. The boundary condition is different from that one. So that is typically the easiest way to do that is with sound and a pipe. Tube that is open on one side, like a beer bottle, and you blow on it. If you do it right, then you create oscillations here of the air, perturbation of the air. The pressure wave propagates down the pipe, but when it reaches this point, the displacement of the air molecules is it's not allowed to change, right? It's pinned because they cannot penetrate this wall. So the water molecules are stopped there, right? So that creates, if you're looking at a pressure wave here, that creates a boundary condition that tells you that one of the possible standing waves that you could have in this kind of system, right, where I'm plotting here, this is the pressure of the air, and this is x, right? The boundary condition that you have to use in that case is that there is no, the amplitude of the wave there is 0, of the pressure wave is 0, and because this end is open, it's equivalent to that end of the wavetable being allowed to oscillate as much as it wants. So this is the pattern that fits that. And you might think, why, if I produce a wave here this way, you know, there will be a wave that is bounced from that end, but what about on this side? Do I get another reflection? The answer is yes. Even when this end is open, which is the case of an open system, you can have musical instruments where they're open on both sides, and you have a wave, you produce a sound perturbation here, it propagates this way. When the sound wave reaches the end of the pipe, it's open now to the atmosphere. The boundary condition, that is not bounded to be moved inside a pipe anymore. It can now spread out. That change in boundary conditions always produces a reflection in any system. If I had a wavetable, two wavetables, one with long rods, and I connected that one with long rods with one with short rods, and I send the wave here, at the interface, because the conditions are changing, at the interface we will always have some of the wave bouncing, some of the wave gets transmitted. So the same applies for this kind of system that are open on both ends. I'm not going to do the math for those. I'm just going to tell you that if you follow the same logic here, one of the possibilities for this kind of systems is antinode here, node here, antinode here, or you can have the other combinations, more antinode, node, antinode, antinode, node, antinode, node, antinode, node, and so on. If you do the math for that, which is following this over there, you get the same equation that we just discussed there. NV over 2L. Okay? You will get it something different for the case when one side is closed, the other one's open. The waves that now match that have the right boundary conditions, the fundamental looks like this. The next one looks like this. You have an open end here, but now you can have this one is, say, n equal 1. So the equation that you end up with is this one. F sub n is equal to 2n minus 1. I need more room there. F sub n is 2n minus 1 factor of v over 4L, where n is 1, 2, 3, and so on. So the first mode, the fundamental mode, has a frequency v over 4L, because n equal 1 is 2 minus 1, 1. So v over 4L. The next one has a frequency which is 3 times that. You can do that, right? 2 times 2 is 4 minus 1, 3. 3 v over 4L. The next one is 5, and so on. So what you get in these kind of systems, open and closed, is only the odd multiples of the fundamental mode. If one is v over 4L, all of the other harmonics are 3 times that, 5 times that, 7 times that, and so on. All right, we'll continue next time.